Cholesky decomposition simplifies complex matrix calculations in mathematics, engineering, data science, and computer simulations. It's ideal for symmetric, well-behaved matrices found in systems modeling, optimization, physics, machine learning, and statistical analysis. Don't worry if it sounds intimidating. We can understand it with simple ideas. Cholesky decomposition breaks complicated matrices into simpler building blocks, making computations faster and cleaner, especially for computers. We use it to solve large systems of equations, like those in bridge design or machine learning model training. These problems involve huge matrices, which are slow and inefficient to work with directly. Cholesky decomposition reduces the workload by splitting the matrix into two simpler, easier-to-handle matrices. Once decomposed, calculations become much faster, which is crucial for efficiency in modern computing. This math shortcut saves time on every computation, adding up quickly when processing millions of data points. To understand decomposition, think of splitting a large task into smaller steps, like baking bread. Breaking it into stages makes it manageable, just as matrices are complicated to deal with directly. Cholesky decomposition splits a matrix into simpler, structured pieces. Imagine reorganizing a tall stack of boxes. If the stack is stable and symmetrical, you can break it into two perfect half-stacks that fit together. Similarly, Cholesky decomposition breaks a nicely structured, symmetrical matrix into two parts that rebuild the original when combined. The half-stack is easier to move, just like the simpler matrix from Cholesky decomposition. Cholesky decomposition is used in many fields. In machine learning, it speeds up solving large systems of linear equations for model training. It accelerates algorithms like linear regression, Gaussian processes, and variational inference, helping models learn faster. In engineering and physics, engineers use matrices to model structures, fluids, and electrical networks. Cholesky decomposition provides a stable way to solve these equations, ensuring reliable simulations. Financial modeling uses Cholesky decomposition for risk analysis, portfolio optimization, and pricing models, helping simulate asset movements. In computer graphics, it solves systems for simulating movement, forces, shading, and visual effects in rendering and animation. Robotics and control systems use it for fast prediction and stabilization calculations, enabling real-time sensor data processing and motion path calculation. Cholesky is preferred over other methods because it is efficient, significantly cutting computation time. It's stable, avoiding numerical errors, and memory-friendly, requiring less storage. It's easy to apply in Python, C++, MATLAB, and R, which is crucial for large-scale systems. Cholesky decomposition can reduce computation by half or more, valuable for large datasets. However, Cholesky decomposition only works on symmetric matrices, where values mirror across the diagonal. They must also be positive and well-conditioned, without instability or negative values. Many problems naturally produce such matrices. When these conditions are met, Cholesky decomposition is one of the best tools. Otherwise, other decompositions are used. But when applicable, Cholesky is typically the fastest and most accurate choice. It fits into computing by enabling huge numbers of matrix operations. This includes weather forecasting, AI model training, 3D graphics, medical imaging, and network analysis. Cholesky decomposition ensures these operations run smoothly and efficiently, playing a major role in making technology fast and reliable. In summary, Cholesky decomposition breaks complex matrices into simpler parts, making large systems of equations faster to solve. It's widely used in machine learning, engineering, finance, robotics, and scientific simulation. Think of it as taking a complicated, symmetrical structure and splitting it into simpler, easier-to-work-with components. Cholesky decomposition is a powerful shortcut that makes big mathematical problems faster and more efficient to solve in modern computing.